And Justinas will talk to us about a recent paper that they wrote on the double copy relations in massive theories. Thanks very much for accepting the invitation to talk, and take it away.
Okay, so thanks for inviting me, and I'm gonna talk a little bit about our recent work in Imperial College London on massive double copy in collaboration with Arshia Momeni, Andrew Tully, and Mariana Carrillo Gonzalez. So the most famous and the most studied example of this double copy relation is between Yangmos and gravity scattering amplitudes, which turned out to be a very useful tool in simplifying various calculations in GR. However, over the years, people have found some other examples of this relation between different theories. For example, nonlinear sigma model and special Galilean, or various supersymmetric theories, gauge theories and gravity theories with higher derivative operators, and many more. So then this raises a question: why are these theories special? Why can we relate them by this double copy? And what we were looking particularly is massive theories. Can we find a massive examples of double copy, the relation between massive spin 1 and massive spin 2 theories? And if that was possible, maybe we could simplify some calculations in massive gravity. And there's recently been some related work on this topic, which is double copy with massive matter by many people. So what we started with was massive Yang-Mills theory, which action is given here. So we have just Yang-Mills term F square and gauge symmetry breaking term M square A square. And we checked whether this theory is related to ghost-free massive gravity, the RGT massive gravity, which its action is given here. And in this action, we have these diffeomorphism breaking operators that give mass to the graviton. And in this action, we have two free coefficients. So two of these kappas are free. So one thing about these theories that they are both effective field theories, which means that they are only valid up to a certain energy scale called the cutoff of the theory. And for massive Yang-Mills, the cutoff is given by this expression, mass divided by coupling constant, which you can think of as this is the mass of massive Higgs field, which has been integrated out from Yang-Mills Higgs theory to obtain this low energy effective field theory of massive Yang-Mills. So for massive gravity, the cutoff is this lambda 3, which is this combination of graviton mass and Planck's mass. And we don't know whether this effective field theory comes from something like gravitational Higgs mechanism. And one thing about effective field theories that people often talk about is so-called decoupling limit, which is the high energy limit of these effective field theories, where the energy is large, but it's still within the validity of the effective field theory. So the energy is still smaller than the cutoff scale. So we just focus what happens close to the cutoff. And in this limit, usually this theory is greatly simplified because some of the degrees of freedom decouple. So if we look at the decoupling limits of these two massive theories, then we'll see that there is some suggestion that there could be a double copy relation between them, because the decoupling limit of massive Yang-Mills is nonlinear sigma model, while the decoupling limit of massive gravity is a Galilean theory, a certain scalar theory. And it is known that for one specific choice of the parameters in Galilean theory called special Galilean, it is a double copy of nonlinear sigma model. So if this extends beyond the decoupling limits, then these two massive theories should be also related by a double copy. So we started with just free theory, just looking what kind of states we would get in this massive spin 2 theory by doing double copy. So for that, we had to decompose a product of two massive spin 1 fields, these massive gluons, into irreducible representations of the massive little group, which in 4 dimensions is SO3. So by doing that, we get this H field, which is massive graviton, then this massive 2-form field, which in 4 dimensions it describes the spin 1 particle, and we have the scalar phi. So we already see that there is some difference between, even at free theory, between a massive double copy and massless double copy, because in the massless case, we get massless graviton and two scalars. In the massless case, this 2-form field B is describing a pseudo-scalar, so spin 0. But in this case, it describes a spin 1 field. So the next thing was to look at the 3-point amplitudes. And for Yangmos, for massive Yangmos, the structure of the 3-point amplitude is the same as in massless case in terms of polarizations and momenta. But for massive gravity, only this first line here is the same as in massless case. So this first line can already be written as the Yangmos 3-point, well, it's proportional to Yangmos 3-point function squared. So if we want double copy to work, we need this to make sure that this extra piece is 0. So that fixes one of the free coefficients in the massive gravity action, this kappa 3, to be -1. So we can make, by doing that, we can make double copy work at 3-point. Then we went on the 4-point amplitudes, and the double copy prescription for 4-point amplitudes is this. So we write the gauge theory amplitude in this particular form where C's are color factors. They are products of structure constants, and kinematic factors. They depend on our interactions of the theory and polarizations, momenta. And STU are the S minus m squared, T minus m squared, U minus m squared are the propagators in our theory. So the color factors satisfy this Jacobi identity. They add up to 0. And by double copy prescription, we need to find the kinematic factors and such that the same Jacobi identity is satisfied by them. So ns plus nt plus u should be 0. And by calculating the massive Yangmos scattering amplitude just from Feynman rules, we found that these ends that we got directly from Feynman rules already satisfy the Jacobi identity, which means that we can use them directly to do double copy. So we just replace the color factor C's by these kinematic factors N's, and we can construct different scattering processes in the double copy theory. So for example, when we constructed the massive graviton scattering, we found its the double copy answer to be equal the sum of these two terms. So the first term is just a scattering amplitude in pure massive gravity, which contains diagrams like these, just massive graviton exchange. But both of these free coefficients, these kappas, are fixed. And there's another term, this extra term, in the second line, and it describes the different channels of scalar exchange. So you remember, we also have a massive scalar in this theory. And we see that in this massive case, we have graviton-graviton scalar interactions, which means that we cannot truncate theory such that we get rid of this scalar as we can at tree level in massless case. So there's another difference from the massless double copy here. So this is just graviton scattering, but remember we have all these extra, these other fields. So our fields were H, graviton, B, spin 1 field, and phi. So we had to consider all possible scatterings of these fields on the external X. So this represented by this J. J describes what is the spin of the external state, and lambda is its helicity. So to construct all possibilities, all processes like this, we had to combine two copies of massive Yangmos amplitudes. These two copies were weighted with Clebsch-Gordon coefficients. So when we did that, we had all possible 3-point and 4-point amplitudes in this double copy theory, and we could construct an action matching all these amplitudes up to this order. So when we did it, we found that we can reproduce these amplitudes by this long action, which we found has lambda3 cutoff, as expected for massive gravity theories. So there's a lot of terms, but this first line here describes massive graviton. Then we have this massive scalar. We have this massive spin 1 field, which previously I wrote V, but we can dualize it to describe just a vector field A. And we have many different interactions between these three fields. So the next thing was to check the decoupling limit and check if it actually gives special Galilean as expected. And what we found that that's not true. When we took the decoupling limit of this action, it turns out that this is not a special Galilean, but a certain bi-Galilean theory coupled to spin 2. And this means that this massive double copy prescription has some discontinuity in high energy behavior because it does not commute with taking decoupling limit. So if we took the decoupling limit of massive Yang-Mills first, we would have obtained a nonlinear sigma model and a double copy of nonlinear sigma model, a special Galilean. But this is not a special Galilean. So there's some discontinuity, something going on in high energy behavior of this massive double copy prescription. So we then try to understand where this discontinuity comes from, and it turns out that the reason for it is color kinematics duality, which is this requirement that the kinematic factors should satisfy the same relations as color factors. And these ends that we found from Feynman rules that they satisfy the Jacobi identities, they had this sigma term, this term which have 1 over m cubed. And in decoupling limit, this term is divergent because in decoupling limit, we keep lambda fixed. So for example, 1 over lambda square would be g square over m square. So this term would be finite because it's 1 over lambda square. And the 4-point amplitude is proportional to g square. So we can only have 1 over m square terms that are finite in the decoupling limit, but something like 1 over m cubed in the amplitude would go to infinity in decoupling limit. So we see we have these terms that diverge in the decoupling limit. But of course, in the gauge theory amplitude, they must cancel out once we simplify the expression, and of course they do by the Jacobi identity on the color factors here. So really this sigma term doesn't contribute to the massive Yang-Mills amplitude. However, if we want to do double copy, we need to keep them inside ends for color kinematics duality. And we need to square ends that contain these sigmas. And once we do that, these sigma terms contribute as this 1 over lambda 3 to the 6th term in the massive gravity amplitude, which is fine in the decoupling limit of massive gravity. So really this term is not, it's only divergent in the decoupling limit of massive Yangmos, but it cancels out, so it's not a problem. But we can now see that this sigma term is really responsible for this discontinuity decoupling limit, because if we start with massive Yangmos, when we take the decoupling limit, we must cancel this sigma term out, otherwise we get divergent pieces. So we cancel it out, and then we get nonlinear sigma model, which by doing double copy gives special Galilean. But if we start with massive Yangmos and do double copy first, we need to keep sigma term for the color kinematics duality, and then we get this long action of massive gravity. When we take the decoupling limit of it, we get this bi-Galilean theory in which the sigma term survives. So it means that the sigma terms basically describe the difference between bi-Galilean amplitudes and special Galilean amplitudes. Then the next step was to look at 5-point amplitudes. And at 5-point level, we immediately encounter a big problem, which was first found by this group. And the problem is that we have spurious poles. And to explain the origin of these spurious poles, I'm gonna now describe this double copy procedure in more general, more formal way for any endpoint amplitudes. So in gauge theory, we can write endpoint amplitude at tree level in this matrix form. So G is just the coupling. C is the vector with color factors. So for example, at 4-point, it would be CS, CT, CU. D is a diagonal matrix with all of the propagators in our theory. So in 4-point case, it would be S minus M squared, T minus M squared, U minus M squared on the diagonal. And N is a vector with kinematic factors. So to impose the color kinematics duality, we need to write all the Jacobi identities, and we can write them in this matrix form as some matrix M acting on the vector C is 0, where this matrix M contains elements with equal to plus or minus 1. And if this is satisfied for color factors, we need the same identity to be satisfied for the kinematic factors. So we need Mn to be equal. Once we find this kinematic factor satisfying this equation, then we can replace C by N, and we get endpoint double copy amplitude. But if we calculate these kinematic factors directly from Feynman rules, usually they won't satisfy the Jacobi identities. So we'll have to change them, we'll have to shift them. But this shift has to be, it cannot change the amplitude, because it is like a gauge transformation or a field redefinition. So it has to be of a particular form. And this form is this equation 2. And we can see that if we choose delta n to be of this form, where v is some arbitrary vector, then the amplitude is indeed going to be unchanged. And why is that? Well, if we substitute this back into the formula for A, here the D will cancel out, and we're gonna have C transpose acting on M transpose, which is MC transpose, and that's equal to 0 by the Jacobi identities. So indeed, this is the correct form which we need to choose if we want to keep the amplitude unchanged. And then we impose the Jacobi identities on the shifted kinematic factor, so n plus delta n. So we need to choose the form of delta n to be as an equation 2, and that gives this equation 4 that we need to solve for v if we want to find the shifts. So this is a matrix equation, but usually this matrix MDM transpose, it's gonna have some non-zero block, which we call A, and all the other elements will be 0. And the size of this non-zero block A is going to be the number of Jacobi identities that we have. Then we can solve this equation for that block. So we need to invert this matrix A. And this has to act on this vector U, where we call vector U the non-zero elements of Mn. So basically, U describes the violations of all the Jacobi identities that we have. Then, once we find these shifts, we can substitute these shifted ends into the double copy amplitude. And by doing some algebra, we end up with two terms. So the first term, this ND minus 1n, it's perfectly fine. It only has physical poles because this D contains the same poles as in gauge theory amplitude. So this term doesn't have any spurious poles, but the second term, it has this inverse of some matrix A. And this matrix A, this DM transpose, remember that D contains the propagators in our theory. So in general, it's going to be some matrix with the entries polynomial in all the Mandel systems that we have. And in general, if we invert such matrix, we're going to have some polynomials in the denominator because the inverse of a matrix is proportional to one of the determinant of A. And in general, the determinant D is some complicated polynomial. So of course, in a physical local theory, we cannot have any amplitudes that have these random polynomials in the denominator. All the poles should be simple poles given by factorization. So for example, in massive Yangmos, this determinant of A is this big polynomial given here, which of course doesn't factorize in the product of physical poles. So we have a problem here. This doesn't give a physical amplitude. So we can look at some theories which we know double copy works, and we can look how these theories avoid the spurious poles problem. For example, just massless Yangmos. What happens there? So in that case, we find that at 5 point, this matrix A is singular. So the determinant is 0. And if you want to solve for the shifts, if we want to satisfy color kinematics duality, we need to invert A in the subspace orthogonal to all the null vectors. But we can only do that if this vector U is orthogonal to the null space of A. So we need all of our vectors to be in the subspace orthogonal to the null vectors. And in that subspace, A might be simpler. And for example, in massless case, the A has rank 5. So in this 5-dimensional subspace, its inverse is much simpler, and it only has its determinant is a product of physical poles. So there are no spurious poles in that subspace. But still, the interactions, these U's, have to be of particular form such that they are orthogonal to the null vectors. And these conditions, these are known as BCG relations. So for example, in 5-point Yangmos, we have 4 null vectors of A. So we have 4 BCG relations that we need to satisfy. And of course, if we check it explicitly, Yangmos theory satisfies these relations, and double copy is physical. So we can copy this prescription, this massless double copy prescription, to the massive case, but we need to our theory to have multiple different masses. And in that case, we can choose these masses such that all the relations between propagators in this massive theory are the same as the relations of massless propagators. So for example, at 4-point, the massless propagators ST and U would add up to 0. But in massive case, if we have different masses in exchange in each channel, M12, M13, and M14, we can choose them in a particular way such that these massive propagators add up to 0. And if we ensure that this is true for all endpoint scattering, then of course for any endpoint scattering, the rank of this matrix A is going to be the same as in massless case. That's going to be the same number of BCG relations. And if we construct the interactions such that these BCG relations are satisfied, then we're going to have a massive theory which is compatible with double copy. And these conditions of masses are called spectral conditions. They were first found by this group. And what are examples of such theories satisfying the spectral conditions? And the obvious example is Kaluza-Klein theories, in which the propagators are based the same relations as massless, because of course they are really massless propagators, just in higher dimension. So what we try to do, we try to take this gauge theory, this Yangmos theory with high derivative operators in 5 dimensions on 4-dimensional flat space times a circle, and we compactified it down to 4 dimensions. And then we obtained Kaluza-Klein theory, which of course is compatible with double copy, but we deformed that theory. So we kept the spectrum the same, but we changed the interactions between different fields. So, and then we try to check whether the BCG relation can still be satisfied for this deformed Kaluza-Klein theory. So this looked something like this. By compactifying, we obtain a lot of different operators. Our spectrum was a massless scalar field, massless spin-1 field, and a tower of massive spin-1 fields. And we had a lot of different operators describing different interactions, but rather than keeping the couplings all related to the 5-dimensional couplings, we put all the couplings of these operators to be arbitrary. And then we ask, can we find a theory which is not Kaluza-Klein theory, for which these BCG relations would still be satisfied? And for that, we had to calculate the 4-point amplitudes, where the diagrams look like these, as well as 5-point amplitudes. And the constraints that we got from that looked like this. So the products of couplings between different fields had to be related. But here, just from analyzing single scattering process, it seems that there should be a lot of freedom in deforming these couplings, because we can scale one coupling by something and scale another coupling by 1 divided by that, and this should still be satisfied. However, when we combined all processes, all 4-point scattering processes, we found that in order to satisfy BCG relations for all of them, we almost have to fix all of the free coefficients to be the same values as in Kaluza-Klein theory. So this G, small g times big G, except for one coupling. But when we combine these 4-point constraints with 5-point constraints, we found that even that freedom, single coupling freedom, is eliminated. So what we got is just that the only way to satisfy all the BCG relations is the original Kaluza-Klein theory, which seems then that maybe these spectral conditions are too restrictive if we want to find some new example of massive double copy, which is not Kaluza-Klein theory. And then we looked again at this spurious pole that we got in massive Yangmos. And it turns out that the spurious pole, this random big polynomial that I showed before, it has some structure. It's not completely random. So this P can be expressed as the gram determinant of 4 out of 5 of the external momentum in our 5-point scattering. And this gram determinant is only non-zero if we work in the dimension of spacetime greater than 3, because in 3-dimensional and lower, we just don't have enough directions to have this determinant non-zero. So maybe this suggests that we have to look at lower dimensions, in particular 3D. That's what we did. So in 3, the matrix A is singular because its determinant is 0. This gram determinant is 0. So we found that it has one null vector, this E0, and it can be expressed in terms of these products of Levi-Civita tensors with momenta. So if there's one null vector, it means that at 5-point there is one BCG relation that we need to satisfy for color kinematics duality to work. So this BCG relation is given here. So our vector U has to be orthogonal to this null vector E0. And what we found that if this relation is satisfied, the single BCG relation is satisfied, then there are no spurious poles in 5-point amplitude. And now I'm going to try to explain why that's the case. So the simplest way to see what's going on is to consider pseudo-inverse of A. So we add some epsilon times identity matrix to A and try to find the inverse of this matrix. And the inverse of a matrix can be expressed as a matrix of cofactors divided by the determinant. And by doing explicit calculation, we show that the determinant of this A plus epsilon I given by this expression 14. So it's proportional to epsilon because in epsilon goes zero limit, of course, A is singular. And the matrix of cofactors has this form. So the important thing to note is that, as I explained before, in the double copy formula, we're gonna have a term which is U transpose A minus 1 U, which in this case is gonna be proportional to U transpose C U. So really this C is gonna be contracted with 2 U's. And we see if we do that we're gonna have factors U dot E0, a lot of factors like this. And by BCG relations, we require that U dot E0 is 0. So this is our BCG relation. And if we require that, we see that these terms won't contribute because they will be contracted with U, as well as these terms won't contribute. So we only end up with this single term K in the numerator, this matrix K. And also we see that this epsilon will cancel out the epsilon in the denominator, and E0 square will cancel this E0 square here. So which means that the only factor remaining in the denominator is going to be this product of these, and these are the physical poles. So this already seems much better. It seems that we only have product of physical poles in the amplitude, but still there is this matrix K, and the expression of matrix K contracted with these U's is given here. So the first line seems that it only contains physical poles because these are the propagators. So the first line is just simple poles, which of course doesn't have any spurious poles, no problems here. But in the second term, we found that we need this product of 2 epsilons in the denominator. And remember that epsilon, the Levi-Civita multiplied by another Levi-Civita can be expressed in terms of products of metric. So really, this product of two epsilons with a moment is going to be polynomial in Mandelstam variables. And this seems like a spurious pole again. But actually, the residue of the spurious pole is 0. And this is because of this structure here. So this Q, these polynomials Q, they are really just factors linear in the components of U. And these 6 vectors EI, they are polynomials in Mandelstam variables. And in general, U dot EI is not 0, but it turns out that for special kinematics, where these two epsilons go to 0, either this epsilon go to 0 or this epsilon go to 0, there's something special happens. So for these special kinematics, we can find these vectors EI such that they are parallel to our null vector E naught. So which means that in this expression, if on the residue of this spurious pole, this will be proportional to U dot E naught, which by BCG relation is 0. So again, BCG relation ensures that there are no spurious poles at all. The only poles are these simple poles, physical poles here, which says that the single BCG relation is enough to ensure that our double copy amplitude is physical at 5 point, which is quite different from the massless case, because in massless case we had 4 BCG relations that we had to satisfy. So
I'll just ask a quick question.
Yeah.
So if you go back to the previous slide, it doesn't look like these amplitudes have a sensible massless limit. Is that true? Or is there a way to see that they do?
Yeah, I think even in this case, it's just like in the 4-dimensional case, there's still discontinuity in the massless limit.
But why should there be a discontinuity in the massless limit? I mean, if you just construct an amplitude of massive gravitons, you'd expect it to completely vanish in the massless limit, right?
Well, it's
in 3D.
just, yeah, that's true. But there's something about the double copy prescription that we need to add these terms that are singular in the decoupling limit in order to satisfy color kinematics. So
Right.
Yeah, that's true. But
certainly we found that if you, in the matter case, it's not necessarily true that there aren't spurious poles. There are spurious poles, but they actually turn out to be physical.
Mm-hmm.
And you can kind of imagine this from the double copy. And this is a question that I always thought about trying to answer, but couldn't. And that's that if you just take 2-to-2 gluon amplitude in 3D, massless, and you square it, what do you get?
Yeah.
Can't be 4 gravitons, right? Because there are no massless gravitons.
Yeah.
It should be something, right? Yeah, and it has to be gravitational probably. So it's probably like some dilitons.
Yeah.
And that's because photons and scalars are kind of interchangeable in 3D if they're massless. But somehow you, certainly in the matter connected case, you can take the massless limit of the graviton and you get this dilaton. And actually, you can just see that from the propagator structure in topologically massive gravity, that there is this dilaton which shows up in the massless limit, but only in the massless limit. But it requires that you leave these 1/m squareds that you've got here. They should actually be written as m squared, 1/q squared, basically, and they're sort of left off shell somehow. And it always confused me how this was going to come about in this story where you make everything on shell.
Right, I see.
So you're saying that this doesn't have a massless limit, so you're just treating everything as strictly being on shell massive.
Yeah, I mean, yeah, that's a good question. I mean, there's the way we do double copy. If we try to take massless limit, then it depends whether we take the massless limit before doing it or after, and then we're gonna have different results.
Yeah.
So yeah.
Okay, cool. Thanks.
Yeah. But anyway, in this purely massive case, if you not consider this problem with the massless limit now, we see that the single BCG relation removes all the spurious poles at 5 point. So what could be a possible example of a theory satisfying this BCG relation? And it turns out that topological massive Yangmos does satisfy it. So it's this theory where we have F-squared term as well as Chern-Simons term, and it describes a single massive parity breaking spin 1 degree of freedom. And so this theory satisfies the BCG relation. It can give a sensible massive double copy. And if we calculate that double copy, we did this at 3, 4, and 5 point amplitude level. And we found that these amplitudes can be matched with the amplitudes of topological massive gravity. So this term has the negative Einstein-Hilbert term as well as this gravitational Chern-Simons term. And this is a very similar theory. It describes a single massive parity breaking spin 2 field. And the double copy matches the amplitudes of this theory at least up to 5 point. So it seems that these two theories are related, and also there was a related work by Nathan, William, and Daniel on the double copy between these theories with matter, which further strengthens this conjecture that there could be some double copy relation at all endpoint scattering, maybe even at loops. So here are some directions for future work. So we could continue looking for some other massive spin 1 theories which are compatible with color kinematics duality with no spurious poles. We could try to find whether topological massive Yangmos and topological massive gravity are related at 6 point and beyond that. Also, there are interesting supersymmetric extensions of these two theories, and it would be interesting to see if they are related by double copy. And also, we could continue looking for possible different classical solutions that are related in these two theories. Yeah, so that's it for my talk.
Thanks very much. Any questions? Could you, if not, I have a question. Could you say something more about the supersymmetric versions that you're thinking of?
Yeah, so there was a paper on n=2 supersymmetric Yangmos theory, this topological massive Yangmos theory, and there are some known supersymmetric topological massive gravity theories. And one thing that we could do just to try to see if they are related or not.
So this is in 3D or?
Yeah, in 3D. Yeah, that's true. It's these topological massive theories. They are only described in 3D.
Mm-hmm. Oh yeah, right. Right. You said topologically massive. Sorry. Okay. Good. Any other questions for Justinas?
Yeah, maybe I've got one. Is there any way to think about the double copy? Well, Is there some way to think about this in a Kaluza-Klein sense as being a reduction from 4 dimensions?
Oh yeah, that's a good question. Yeah, so for this topological massive theories, right? Yeah, so in the original paper, yeah, there is a connection between these 3D theories and 4D theories with some topological terms, in which one dimension is integrated out, but it's not Kaluza-Klein reduction. It would be, we have some different dimensional reduction. So it could be, yeah, it could be some connection with 4-dimensional theories, but it's not Kaluza-Klein. It's not reduction on a circle.
So do you mean here that you'd start off with some Maxwell plus theta term in 4 dimensions and reduce that?
Yeah, well, yeah, Yangmos, I guess, plus a theta term, yeah.
Because I actually showed at some point that you can take, at least in spin helicity, you can take and in fact, I think it's in our Anion paper, you can show that the polarization vector, like just say 4-dimensional, spin 1 or whatever polarization vector, you can just do a dimensional reduction along one direction, make that direction massive. Now, I didn't, specify that it was done by a Kaluza-Klein or whatever. I just, randomly said, I'm going to turn this component of the momentum into M. You can show that the polarization vector that you get at the end, you can reproduce, for example, the light cone gauge propagator for topologically massive Yangmos. Exactly. All the terms, right? So it, in some sense, the like topologically massive is a natural extension of just spin 1, massless spin 1. You can just go from massless spin 1 to massive spin 1 in 3D. So it seems like there should be a simple way to just do it to all, like to the amplitudes in general. Like you should be able to just take, massless gluon amplitudes and get massive 3D, topologically massive 3D amplitudes, just kind of automatically. I never went further trying to think about how you do it to a whole amplitude, because somehow you have to dualize all the legs or something like that. But
yeah, that's true.
In principle, it seems like a plausible idea. But
yeah, that's a good point. Yeah, and yeah, it's not completely clear. I mean, whether this in the 4 dimensions it should be just pure Yangmos plus some topological term, because the way double copy works in this 3D theory is quite different. Like the number of BCG relations is just 1 at 5 points, and these null vectors have completely different forms. So, but yeah, I mean, I would expect that there should be some story with the relation to 4-dimensional theories.
Great. Any other questions? If not, thank you, Justinas, again for a really good talk. That was a fantastic introduction to the material as well as to your paper. Again, thank you very much.
Thank you for listening.
yes.